Now I get to enjoy 30 or 40 minutes of talking about the scientific life of Charlie Misner. This talk will be just some scenes from his life, scientific life. In preparing it, I looked through his whole publication list and looked at some papers and lamented that I didn't have more time to read about more things that I hadn't actually ever dove into enough. He's a man with a delightful, creative, and sort of passionate scientific mind. And I hope you'll get at least a little bit flavor of that from the scenes that I'm choosing to show you, but be aware that, of course, I'm leaving out huge amounts. So why isn't this advancing? Where should I point it?
Push the, there, it's down. It's
oh, okay. The opposite from what I thought. Okay.
Could you move your microphone up a little bit?
Yes. Like that? Then I can stand and see what I'm looking at. Okay, so this is a NASA ADS website. You can find all the scientific papers going way back. I used that to list Charlie's first few publications. Actually, one of them is slightly out of order here. So the very first publication is his senior thesis, his PhD thesis, which most people didn't even know in the field was on Feynman quantization of general relativity. This was like the first look at how to use the brand new method of approaching quantum mechanics that Richard Feynman invented and use it to try to understand general relativity. And the themes that Charlie uncovered in that, which had to do with the role of topology in general relativity, the important role of invariance under all coordinate transformations, and the strange description according to Hamilton's equations, all came up in that first paper. But he didn't actually go that far down that path in the paper. It's an extremely difficult problem, which remains unsolved today, applying that approach to quantizing general relativity. Then, of course, there's the very well-known work with John Wheeler on the geometrical description of empty space-time as a interesting structure. They called it geometrodynamics. And Charlie went on to develop that as well. His first paper with another, I guess, student at the time, maybe, or a young faculty member, David Finkelstein, was on some new conservation laws, which I'll show you a picture from in a moment. This led directly into the idea of a black hole horizon. And the wormhole initial conditions refers to the work started off with Wheeler about exploiting the possibility in general relativity that space is not just an ordinary Euclidean like plane in one higher dimension, but can have holes in it and bypass routes through wormholes. So I'll mention a paper on that as well. I wanted to start by just mentioning super quickly, kind of for the relativists in the audience, what this paper is about. I didn't know it before. They address a paradox in there, which is, according to general relativity, it turned out that not only does energy source gravity, but also pressure does. And for that reason, if you have electromagnetic radiation that has pressure, a significant amount of pressure as well as energy, it creates more gravitational pull than just the equivalent amount of energy. In fact, twice as much if the radiation is isotropically distributed, the electromagnetic radiation. So they asked the question, what if I have some mass there, let's say a particle and an antiparticle, and they annihilate and turn into radiation? The same amount of energy is there, but suddenly there's all this pressure, so it looks like the gravitational field should suddenly double. And that's clearly nonsense because the total energy didn't change, so it must be that looking at it from far away, you can't tell that the mass energy turned into radiation energy. So that was a paradox, which they solved. I won't tell you the solution, no, okay, I will. The solution turned, what?
I'll tell them in my.
Oh, okay, then I'll leave it out. Oh, but some people will only be here this morning. So as a teaser, it's important to keep in mind that the radiation, if it's going to remain in the location where the mass was initially, it must be contained by a container. And the container also creates a gravitational field. You can do the rest. Steve. That's Steve Carlip. Okay, so moving on. This is the paper on wormhole initial conditions. This one was written in 1959. This is a picture of one of these kind of objects that Johnny Wheeler and Charlie were thinking about, where space has a wormhole connecting one place to another. Kip Thorne mentioned this kind of thing in his talk yesterday. And the thing that Charlie does here is actually find a solution to Einstein's equation that describes this object at an initial moment. And the way he found the solution, I just wanted to say for the sake of those who could understand a couple of words about it, is a just very elegant, simple way that is delightfully surprising that you could do it. He started out with this line element, which describes what he called a three-dimensional donut, which is a circle across a sphere. And then he just applied, he took that donut line element, D for donut, W for wormhole, and multiplied it by the fourth power of a scalar field. So this is called a conformal factor. And it's possible to choose that function so that Einstein's equation is satisfied for this as an initial condition. But actually, it won't remain that way. This thing would evolve in time once you let it go, according to the equations of general relativity. And Charlie analyzed verbally, kind of in this short paper, what would happen to this object. He reasoned he could actually evaluate the mass of these things, how much mass they appear to have if you're outside of them, how far away they are, how much mass the whole object has, and how long it would take for it to collapse. But one line I love from the paper was this one: the possibilities for obtaining information about the time development of this wormhole metric by using an electronic computer are being investigated by R.W. Lindquist. So I'm sure that somebody in this room knows whether this calculation was ever in fact done on a computer. I imagine it has by now. Great. Perfect setup. I didn't know that. We didn't plan this at all. That's Kip Thorne, for those of you that don't know him. Okay, so I wanted to dive a little bit more into this Charlie's awareness of the potential or the promising role of computers in general relativity all the way back in, all the way back in 1957, which was, I think, 2 years after he started graduate school or something like that. There's a famous conference in Chapel Hill on the role of gravitation in physics. The proceedings of the conference are available, actually completely free online now, with including papers given and discussions between the people there. One of the discussions at the end of a talk was Charlie had the responsibility of summarizing the discussion of this session, which had to do with solving the equations for the initial conditions in general relativity. And because it's so great, I'm going to actually read quite a bit of this paragraph. Just to show you that Charlie was there in 1957 thinking about the future of computers in general relativity and what they could do for us, which they indeed have done. So first, we assume that you have a computing machine better than anything we have now, and many programmers and a lot of money. And you want to look at a nice, pretty solution of Einstein's equations. He's a little kid saying this, right? I don't know how old he was, but in his early 20s. The computer wants to know from you what are the values of the metric and its time derivative at some initial surface, say t equals 0. Now, if you don't watch out when you specify these initial conditions, then either the programmer will shoot himself or the machine will blow up. In order to avoid this calamity, you must make sure that the initial conditions which you prescribe are in accord with certain equations at the initial time. These are what are called the constraints. They're equations analogous to, but much more complicated than Maxwell's equation that says divergence of the electric field is 0. They're the equations to which we have been finding particular solutions, like his wormhole and the ones in the previous talk of this meeting. Madame Fourès has told us that to get these initial conditions, you must specify something else on a two-dimensional surface and hand over the problem of the initial values to a smaller computer first, before you start on what Lichnerowitz called the evolutionary problem. The small computer would prepare the initial conditions for the big one. Then the theory, while not guaranteeing solutions for the whole future, says that it will be some finite time before anything blows up. This guy saw the future, right? I mean, anyway, I love that. So the next scene that I want to mention is the famous ADM collaboration. So ADM is Richard Arnowitz, Stanley Desser, and Charlie Misner. This is apparently all the papers that NASA ADS came up with from their collaboration. The most cited one is the one that was recently, well, that was reissued, republished in 2008, which is the dynamics of general relativity, and it has 1,567 citations as of yesterday, I guess. What is the point here? The point is that Einstein's theory is a theory of space-time. The whole point is that space and time get completely mixed together in general relativity, but I shouldn't really say completely. It is not completely, because while I can move forward in time, I can't move sideways in space. Me as a human being, I'm always going forward in time because I can't go faster than the speed of light. And so if I were to go faster than the speed of light, I could go just in space and not in time. To put general relativity on a computer and calculate, you have to have time labeling each configuration of the system. And so in order to do that, it's necessary to put the theory in a form where it's not space-time, but it's space plus time. And this work is all around facets of how do we formulate general relativity theory in that space plus time framework. In physics terms, it's putting it into the form that Hamilton in the 19th century formulated the theory of mechanics, called Hamilton's equations. And because it's a general meeting and not all relativists, I will not go into details about it, but I hope that those words make sort of clear what is important about this. You might say, why 15 papers on just putting general relativity in the form of space plus time? But there are many facets to it. Some have to do with identifying, like, how do we understand energy in general relativity, and how do we recognize the presence of gravitational waves in a time plus space formulation of general relativity? What about if we reduce it to space plus time in different ways? Do we actually get the same theory? So this is just some of the reasons why there are many different papers here. I wish I could talk about several of them, but I just don't have time right now. This is just a picture of one of the papers, just so you can see what it looks like in the journal. Canonical variables for general relativity. See in their own words what they said about it. The theory is cast into normal Hamiltonian form in terms of two pairs of independent conjugate field variables. These are explicitly exhibited and obey ordinary Poisson bracket relations, and they reach this form by imposing a simple set of coordinate conditions. And then, well, okay, this is quite technical, but the last line is the bearing of these results on the quantization problem is discussed. So that's the one other thing I didn't mention. Another reason to do this is that our understanding of quantum mechanics is based on space plus time picture of the world. And so if we were going to apply quantum mechanics to general relativity, which for the sake of the unity of physics we must do, we must be able to describe general relativity in a space plus time framework. And quantum mechanics had been best understood through this Hamiltonian formulation. So this was like preparatory to applying quantum mechanics to general relativity, which still is being developed many years later. Okay, so going back to the paper I mentioned on the first slide with David Finkelstein, now I'm going to connect to Charlie's work that relates to black holes. So David and Charlie developed the idea of conservation laws that are not really local properties of the evolution, like the flow of charge through a region, charge that goes in, the same amount comes out. That's a local conservation law. But a kind of conservation law that has to do with the global structure of the space or of the field, something that has a twist or a knot in it that can't go away once it's there. And they applied this idea to general relativity, and in the paper, you'll find this picture. So this is a picture of space-time, and each of these little cone-shaped things is actually showing you where light can propagate in the space-time. Something going to the future has to go inside the cone, and something going on the edge of the cone is going at the speed of light. And as I mentioned earlier, something going outside the cone is actually just going spatially. It's not going forward in time, really. So they noticed that you could imagine a space-time, not a real one that we live in probably, but you could imagine mathematically one in which these cones that determine the direction of time flip over like this and twist around. And here's a case where it flips over once. It's up right here, it's up right there, and it's down over there. That's one twist of the light cone, and then you could consider two twists. The point here was that however many twists there were, it couldn't change as time evolved, and that was why they called it a new conservation law. Oops. A second input to, you'll see what this has to do with black holes in a second. A second input to the notion of a black hole, before the word black hole was coined, was in a paper, well, that Charlie, published this in a conference proceedings of the conference called The Nature of Time. It happened at Cornell, I think in 1963, maybe. Yeah. The paper was called Infinite Redshifts in General Relativity. It was studying what happens when a star collapses, and collapses so much that it becomes a black hole, although, like I said, the word black hole hadn't been invented yet, or at least it wasn't in common use. Oppenheimer and Snyder, in a famous 1939 paper, had studied this physical process, but they studied it in equations, basically, and they only looked at what it implied about how it looked to an outside observer who sees a star collapsing that way. And Charlie had the idea that you could understand what they did in a very simple way by putting together the description of a collapsing universe in general relativity with the picture of a static, spherically symmetric solution in the vacuum outside. And he suggested to an undergraduate at Princeton, David Beckendorf, who did his undergraduate thesis, basically implementing this idea Charlie had that you could match a sector of this cosmological Friedmann universe to the empty Schwarzschild spacetime. And Charlie reported on this result with this picture in this conference proceedings. What Charlie seemed to think was the most important thing here was that it allowed you to look inside the black hole and see what it looked like inside. And it's a little bit hard to pick up if you don't know what you're looking at here, but this diagonal line is the event horizon, what we now call the event horizon of the black hole. This is actually material matter that's collapsing to form the black hole. And outside of the striped lines there's a region, it's just a little triangle here, inside the horizon, but outside the matter. And then up here is where the curvature of space-time becomes infinite. And so this allowed you to sort of understand what is going on, not just from the viewpoint of an observer stuck outside, but really what's happening in the entire space-time when an event like this happens. So these ideas fed into two extremely famous papers that were like revelations to the field of general relativity. One is the famous David Finkelstein paper, where he described the event horizon as a one-way or a unidirectional membrane, where influences could propagate only on one way through it, either in or out. He called the paper past-future asymmetry of the gravitational field of a point particle, because there were two solutions. You could either set one up where you could only fall in, or you could set one up where you could only come out. And strangely, David didn't realize, I think, in this paper, that if matter collapses to form a black hole the way Charlie was looking at, it would always, of course, be that you could only fall in. The solution where you could only come out wouldn't describe the physical process of collapse. And yet, it's strange that if you notice that, nobody notices this, but I'm going to point it out now, and hopefully then people will. This is David's picture. And notice that his light cone is tipped outward here. So in this, the solution that David chose to show in his picture is the one where things can only come out, as opposed to the one where things can only fall in. Now, the next picture I'll show you is from a famous paper in 1964 by Roger Penrose. This is probably the basis of the Nobel Prize that Roger recently won, although the prize committee cited him for the wrong reason, which we could talk about at the coffee break. But this is Roger's picture, which is basically like the idea that Charlie presented in that Nature of Time, which shows matter collapsing to make a black hole. Here are these light cones that are tipped over. I don't know if you can see that they're only pointing inward, opposite to that one. And the key point of this picture was that Roger realized that if you go to that region inside the horizon and outside the matter that Charlie had drawn a picture of, there's something very strange about that, which is that if you try to send light going outwards from there, it actually goes inwards. It can't, gravity is so strong that even the outgoing light falls in. And Penrose called that a trapped surface or an outer trapped surface. And it was the key to Penrose proving the first singularity theorem, which is proving that in general relativity under certain physical assumptions, it's unavoidable that the equations will tell you that the curvature becomes infinite. That's a strictly important thing in a theory because it's telling us that the theory is responsible for its own demise. No matter what you do, the theory will break down somewhere, and we still don't know to this day what happens on that singular location in space-time. Okay, jumping to another thing, this is actually a picture of a letter that Stephen Hawking wrote to Charlie. I wanted to show it partly because this brought a huge sum in an auction at Christie's in London, which Charlie donated to the physics department, Charlie and Susanna, to create, I think it's called the Weber Fund, to support gravitational physics research at the University of Maryland going on into the future. The letter is actually readable. It was written in about early 1968. And it's, I guess, probably one of the last things that Stephen wrote by hand, one of the last letters. The point of the letter is talking about singularity theorems. So Stephen learned from Roger Penrose about the idea that you could prove singularities. He wanted to extend it to the case of cosmology as opposed to black holes. And in this letter, he's introducing a new definition of what should be regarded as a physical singularity. He introduced the idea of geodesically bounded. So I'm going to say something technical now for one or two people that might understand it. And since this will be available online in the recording, people could look into it later. But I think the point was that Stephen was trying to avoid the need to assume some causality, this strong causality condition that had been assumed in proving singularity theorems previously. And he thought that he could prove a stronger theorem by instead formulating it through the assumption of, through this formulation of singularity as geodesic boundedness. The reason I think it never was implemented is I looked in Stephen's papers, and I looked in the joint paper with Penrose, and I didn't find this term. Maybe they renamed it. Haven't combed through all of Hawking and Ellis's book, so I'm not completely sure, but maybe an expert can tell us whether this was really a new idea that came to fruition or just an idea that didn't work out so well. Another correspondence I thought was interesting to show is a letter that got typed from Stephen to Charlie. The reason I want to show this is has to do with the discovery of gravitational waves by Weber, which turned out to be not an actual discovery, but people were so excited about it that even Stephen Hawking and his student Gary Gibbons, they're theorists in general relativity, they dropped their theory work and started developing the technology for gravitational wave detectors in England. And so here's what this letter is asking Charlie to help his student Gary Gibbons meet Joe Weber at Maryland and talk about their new design for an upgraded or improved form of gravitational wave detector. So he says that Gary will be attending the APS meeting in New Orleans, and he's going to report on the British work on the design and construction of gravitational wave detectors. We think that without the use of liquid helium, we can improve the sensitivity by a factor of 100. Now comes a real theorist's estimate of the time it takes to do something. The first of these detectors should be operating before the end of the year, and the second one at Reading should follow soon after. Anyway, great letter. Okay, passing to a later stage of Charlie's career. This is a wonderful cartoon that Charlie's student Vishu Vishveshwara had made on the occasion of the 60th birthday celebration we did many years ago, a little more than 30 years ago, for Charlie and Dieter. They both turned 60 in about the same time. And this was the picture made for Charlie. There's also one made for Dieter. And this just shows some of the ideas in physics that Charlie had been working on. It's like good old Charlie's restaurant or hop stand. Here's a mixer. So there's the MTW book. I'll say something about it. We're going to hear from somebody about Taube and Nut, and neutrino nuggets I'll say something about shortly. There's the famous ADM additives, almonds, dates, and marshmallows. This is the cosmology stuff. Mixmaster milkshake. I'll tell you about the Mixmaster and why Charlie was talking about Mixmaster. And I think Steve Carlip will talk about the mini superspace special. And I'll mention why he's saying we use only homogenized milk and isotropical cream. Oops. So the Mixmaster universe. So Charlie, this is after the discovery of the cosmic microwave background radiation. How much time do I not have?
This says you have 3 minutes.
Uh-oh. Okay, in 1965 maybe, people realized, wow, we really have a handle on relativistic cosmology with an observation that tells us fine detail about the strange uniformity of the universe at large scales. And Charlie, in this paper, starts out explaining what's now called the horizon problem. I think it might be the first case of anybody spelling it out in these simple, clear terms. And he proposed that it's a real problem in physics, and it could be solved perhaps by considering more complicated solutions of general relativity, where instead of a uniformly expanding universe, if you go backwards in time, it's uniformly contracting. Actually, it goes into a phase where it's stretching and squeezing in different directions like that an infinite number of times, and that all that stretching and squeezing is what was responsible for making it uniform today. It turned out that idea didn't work, but that was the point of this study that he started. He was also considering another explanation for this on physics grounds, using the fact that the universe is full of matter that can kind of, if the universe is expanding in different rates in different directions, then the matter will flow in different ways in different directions. And the difference in the flow, when it's coupled back into Einstein's equation, would tend to make it more uniform. That was what the point of this study was. And this involved neutrino propagation in the early universe, a much more like physical idea than you normally thought of Charlie Misner as working on, because he was so adept at mathematics and really at everything. People tended to think of him as being mathematical, but this is a very physical study. And he didn't just, it's not just one paper, he pursued this idea. Where it ended up, I actually don't know, but to what extent it could succeed or did succeed.
I could say something about it.
Great. Okay, how am I going to deal with the fact that I've run out of time?
Keep going. I'll talk about this.
So I should skip this one? Okay.
Work in a different frame.
Okay. Yeah, okay, now I'm in a different frame. I want to say a couple of words about the famous book, MTW book. Misner, Thorne, and Wheeler wrote this great book. It's 2.575 kilograms, according to this picture. I just want to say how popular this book was among physicists and non-physicists and remains to this day. A few months ago in Physics Today, this picture appeared. It was in a letter that was sent by this guy. His name is Johnny Powell. This is Alan Bramley, I think. He was just talking about teaching physics in the Peace Corps in Malaysia and how good an experience it was and how physicists should reach out to the world, kind of thing. But I noticed in the picture, this guy is holding the book, Gravitation. And if you go back, it's like he's got a big backpack on, and he's got a big backpack on, a 1970s style backpack, and he's holding the book. So I wrote to Johnny Powell and I asked him, what was going on here? Why was he holding the book? And I found out what his name was, and I got messages from both of them. And here's what they had to say. Alan Braley said, I was probably holding the book as we were coming off a flight, and it was our entertainment. Johnny Powell said, we worked on several problems during the epic train ride from Jakarta to Jakarta. So they were on the Peace Corps travel in Malaysia in 1975. Well, I especially was shocked by this because I had a college classmate in the 1970s who also joined the Peace Corps, and he went to Nepal. And he brought one book with him to Nepal. And guess what book it was? The same book. He went to teach in the mountains in Nepal, and he brought that book with him. I also know that firsthand that it's popular among the general public because my wife Robin's father, who was a Texas oil man, had the book, which I inherited. Okay. And of course, it's never too early to start on track one. This is Mark Kamiankowski's son reading page 212 on parallel transport and its relation to flying from Peking to Vancouver. Okay, should I stop and come back to this maybe if we have room during the discussions, or should I finish my talk?
Well, I hate to cut you off because it's a wonderful presentation. So, but maybe we should take some time now for discussion, I think. And if there's a, you know.
I could just do the rest of my talk in a slot because I don't think we filled all of the remarks time.
Okay, so if time permits later on.
Yeah, I mean, I definitely want to say it, but I think I shouldn't take everybody else's time.
Okay. All right. In that case, let's call it the official end of the talk for this one.
And that does give us time to have some remarks from the audience. Devin, you're looking online to see if there's anybody there. Q&A. So would anyone like to start off with remarks or questions based on what Ted has said? We already had some promises that some of these topics will come back in later talks, which is great. But don't be shy about asking about something. Okay.
Thanks. On one of the papers you showed, his affiliation was in Copenhagen with Arnavit and Dezer. I was wondering how long was he in Copenhagen, and how did they collaborate without email and Zoom over such distances?
Maybe Dieter or Kip knows the story. What I do know is John Wheeler took Charlie when he was very young to Denmark for a research trip, but I don't know the history. Can we give Kip the
papers has an
microphone?
affiliation in Copenhagen for Charlie Misner.
And that was 1959, I think, the date of that paper. Mm-hmm. And so you were wondering how long Charlie was there and how that collaboration.
I think Benedict or the children probably know better than we do.
Benedicta, do you want to answer that? Or Tim, one of you.
Well, one of the things that happened was my father was in Copenhagen because John Wheeler took him there, but Niels Bohr was very interested in young, bright physicists, being surrounded by them. They didn't have to be atomic physicists, but he went to what became the Niels Bohr Institute. But he met my mother and married her, and certainly Stan Dezer, who also married a Dane, And my parents had their honeymoon on the island of Bornholm, which is in the Baltic off the coast of Denmark. And there was a schoolhouse in a town on this tiny little rock of an island, and where an artist lived that my grandfather, my mother's father, knew. But anyway, so they stayed there, and Dezer and my father worked at a schoolhouse there on a lot of what you've seen of the papers. I don't know if Arnowitz came and visited them or how that happened, but they were actually physically together doing it in this little schoolhouse on this tiny island off the coast of Bornholm. So.
Perfect.
Okay, I see a hand in the back. Well, it helps for the people online especially to have the mic. And if you hold the mic close to your mouth, don't be shy.
Thank you. I have two quick questions. The one question is about the golden oldie you had on one of the pictures. So could you please go back to that slide?
The
The ADM golden oldie paper. Like you had a lot of papers there.
right.
Like 10 papers or so in one page. Yeah. So I was just curious. The republication has more citations than in the original.
Yeah.
Is it because of the rise of the computers, or was it it went to MTW, the citations?
That paper, if I'm not mistaken, appeared in a book, which was kind of a report on the status of the field. And when papers are in books, especially in the modern day, and even in the past, it's just harder to go to the library and find the book and cite it. People would tend to cite a journal article rather than the overview of this body of work that appeared in that review article in the book. But once it's available in this form, I assume, but I'm not sure, that it's just because it's so available and so easy to find the citation and put it electronically into your paper, that any paper today that uses this formalism, this methodology, would want to cite, well, where did it come from? And that would be the convenient place to cite it from today. I guess that's why, and I guess the 1567 are since 2008.
Okay.
I don't think it's mixed in with the previous citations, but I'll check in the break and let you know.
Okay, and I was just about regarding the previous question. There's Stanley Deser has a autobiography, and they were saying that they were working on this ADM equations on a blackboard that were designed for little students. So they were like kneeling down, and they were.
Oh, that's what Benedicta was just saying. They were working in a small schoolhouse on that little
they
island.
were on their knees and then writing those equations on board.
I wish there was a picture of that.
Probably the only picture of a blackboard.
And lastly, do you have a quick comment on a neutrino nuggets? I was curious about that.
You mean what it refers to?
Yeah, in the picture.
I think it's that idea that in the early universe, the flow of the universe would have been filled with, among other things, just a bath of neutrinos. And they would flow in different ways if the universe was expanding at different rates in different directions. And he was analyzing, according to Einstein's equation, what would that difference of the flows, what effect would it have on the expansion rates? And he was showing that in general, it would tend to make it less uneven. It would tend to make the expansion equalize in different directions. I believe that's what neutrino nuggets referred to.
Okay, thank you.
Could I make a quick comment, Ted?
Yes.
So you mentioned Madame Flores.
This is Jim Eisenberg.
Yeah, Yvonne Choke. She's turning 100 this December and is still going strong. Still going strong, which is wonderful. In fact, there's going to be a conference in her honor in Vienna in December, which I think would be great to see. She's done some wonderful work. Did people hear me?
I heard you, but I didn't hear everything, unfortunately.
Just that.
And who was it that was turning 100?
Yvonne Choquet-Bruhat.
And still.
So you're saying it just announcing that her upcoming birthday and the conference celebrating it?
There's going to be one in Vienna in the first week in December.
Thank you.
Okay, thanks a lot, Ted, for being